Okay, folks, good morning. Today we're going to be talking about um, area under a curve and how we can compute that with an integral, with an antiderivative. Actually, so far, we've been talking about building a total function from a rate function. So, for example, if they give you a function that's a marginal cost function and they ask you, build the function that will give me the total cost, okay, you would do an antiderivative, you would integrate that function, okay, and then that function can be used to compute a total cost. Now, what we're going to be talking about today is a strategy of finding, let's say, the total cost from one X value to the other X value. You can think of this as, I want to know the total cost of producing my product between Q1 and Q3. You would expect a number out of that, some amount in dollars, okay? The integral or the antiderivative actually computing is the area under the curve. Okay, so what we're going to be talking about today is a mechanism for manually approximating this area. And we're going to be doing that by actually overlaying rectangles on our curve and using those to approximate the area under the curve. Okay. I'm going to be using a combination of things for today's class. I'm going to be using my notes, which are in-course notes and videos. I'm also going to be using Desmos and maybe even Symbolab to kind of show you the tools that you for doing this, okay? At any time, if you've got comments or questions, okay, please just put something in the chat, okay? I'll always have the chat open so I can see your questions. So for now, I'm going to be sharing my screen with you, and it should have my notes. Here we go. Okay, so section 15.3 in our course is talking about area and the definite integrals. So far, the integrals that we've been calling antiderivatives are called indefinite integrals because they just return a function. Okay, and it's up to you to use them to evaluate it at a certain x value. What a definite integral is going to do is it's going to actually return a number that's going to be the area under a curve between an x value, a low x value, and a high x value. Okay, so the way I'm launching into this is I'm talking about finding area of geometric figures. Okay, we usually do that with a formula, right? We have a formula for area of a circle, pi times the radius squared. We have the formula for area of a rectangle, length times width, and so forth, okay? Well, suppose we want to find the area of a region that's bounded by a curve that doesn't necessarily give you a well-defined geometric shape, okay? We can use the definite integral to help us do that. And then, like I said, we can generalize this to kind of be a total value of a function between two x values, okay? So what we're going to be doing is we're going to approximate the region we want to find the area of by overlaying it with rectangles. Finding the area of a rectangle is pretty easy. You just multiply its length times its width. And then again, you would add up all the rectangles that overlap your area. You get a pretty good approximation. Now remember, it's an approximation. It might be too big and it might be too small. Okay, and we're going to look at ways to tell what we've got here. Okay, all right. Example. Let's say I have a region that's bounded by the x-axis down here. Okay, I'm looking at this figure on the left right now. Okay, and it's the graph of the square root of 4 minus x squared. Okay, I realize we haven't talked about relationships that graph as geometric shapes, but what you've got here is you've got a quarter of a circle. Okay, now I can actually use a formula to figure out the area of this quarter circle, right? Because I know the radius is 2, okay? And again, if I just multiply pi times the radius squared, okay, I'll get the area of the whole circle and then just divide that in 4. So I know what the area answer should be. But what I'm going to do is I'm going to approximate this quarter circle by these rectangles. Now, what's important is when you lay out the rectangle, okay, one of it's you either have to put the left top endpoint on the curve, like I'm doing here, or the right top endpoint has to be on the curve, or the middle of the rectangle has to be on the curve. So these, what I've drawn here, are called left endpoint rectangles, okay, because the left top endpoint of each rectangle is sitting on my curve. I need to do that so I can figure out what the height of the rectangle is, okay? If you look at this first rectangle, it's easy to tell its width is 1 because I built it that way. But what's the height? The height is going to be whatever this function returns when x is 0. How come? Because when x is 0, this left endpoint is sitting right on the curve. So this ordered pair is going to be 0. And whatever f returns when I plug in 0. If you take a look at what that would be, okay, if I put in a 0 for x here, I'm going to get the square root of 4 minus 0, which is the square root of 4, which, as you can see from the graph, gives me a 2. So this rectangle, this first one, has a height of 2 and a width of 1. Okay? This second rectangle, if you essentially put its left uppermost corner on the curve, okay, then this rectangle will have a width of 1, okay, and the height of it will be whatever f churns out when you plug a 1 in, okay? Well, let's plug a 1 in. That would be 4 minus 1 squared. That's 4 minus 1. 4 minus 1 is 3. So the height of this rectangle is the square root of 3, okay? Let me stop and ask at this point, is everybody understanding how I'm getting the heights of the rectangles? Okay, everybody understand how this is working? I'm getting the rectangle heights. Okay, good. Right? And again, the reason that's working is because I chose to put the left hand top of the rectangle right on the curve. Okay, it's important when you do these types of approximations, pick the same corner for each of the rectangles. If you're using the left one, make sure all of the rectangles have their left corner on the curve. Okay, so, all right, the height of the leftmost rectangle is 2. Okay, its area is going to be length times width, so 2 times 1. This rectangle will have an area of 2. This rectangle also has a width of 1, and its height was 3, so its area is, I'm sorry, square root of 3. So this rectangle has an area of square root of 3 times 1. So let's take a look at what I've got down here. Okay, so I've got 2 square units for the first one, square root of 3 square units. Okay, so the approximate area under the curve is the sum of those two numbers, 2 plus the square root of 3. Okay, now if you bring up your calculator and you see what that is, let's see if I can bring up a calculator here. Okay, so I have I thought my basic calculator had square root. I'm not seeing it on here. See if I can that to the Okay, there's the square root of 3 plus, and we said the first rectangle was 2. So I'm getting an approximate area of 3.73 square units. Okay. Now you can tell from the picture that I have up here that that's going to be definitely too large because these rectangles hang out over the curve. Okay. It's too large of an estimate. Okay. In this particular example, you could figure out exactly what this area would be. Okay. Because again, I have a circle whose radius is 2. Okay. So the area of the whole circle would be 2 squared. Okay, so radius squared times pi. I'm going to approximate pi. And then divide that in fourths. Because I've only got a quarter of the circle. Okay. So my area for this space, okay, is 3.14. And my approximation was 3.73. So we can see that my area is too big. Okay. All right, so basically this left endpoint overestimates the area, okay? So is everybody seeing how I'm getting the total area? Approximate area. Is that clear how I'm getting the approximate area? Okay, good, awesome. All right, well, let's see if we can figure out a way to get a better estimate. So let's try the same idea using right endpoint rectangles, okay? And then midpoint rectangles. Okay, so here's right endpoint rectangle left. I'm creating rectangles that are 1 unit wide because that makes it easy to do area, okay? And if I put the right endpoint of my first rectangle, okay, where x is 1, it's going to sit on the curve here, okay, at f of 1, which we already figured out is the square root of 3, okay? So you'll notice I can't fit another right endpoint rectangle in here because its right endpoint would be all the way down here on the x-axis. And so the rectangle would have 0 height, okay? So this estimate for area under the curve is the square root of 3, which is about 1.7, and that's way too small. Okay? The only other thing I can do is find midpoint rectangles. These are a little trickier because I have to use the middle of the rectangle as the point that sits on the curve. That means to find the value, I have to plug in 0.5 to my function, okay, to get the height of this rectangle. And for this rectangle, I have to plug in 1.5 to my function, okay? That's this function up here, okay? The square root of 4 minus x squared. So I'd plug in 0.5 for the first rectangle and 1.5 for the second rectangle. Okay. And I have the calculations down here to kind of save you the trouble. Okay. For the left endpoint rectangle, I could only fit 1, and it has a height of the square root of 3. The rectangle is 1 unit wide. So the total area that I've approximated under this curve is 1.7321 square units, which is way too small. Because remember, our exact answer is pi. It's 3.14 square units, and that underestimates the area. Let's take a look at with midpoint rectangles. Here I'm plugging in 0.5, okay? That gives me the square root of 3.75. And then for the second rectangle, I'm plugging in 1.5. That gives me the square root of 1.75. Again, the widths are 1, so I'm just multiplying both of these by 1 to get an area. This gives me approximately 3.2594 square units. Well, that's certainly a better approximation than the left endpoint rectangles. Remember, they gave me 3.73, which was way over. The midpoint rectangles, if you look at them, they don't hang out as much over the curve. And then there's this little piece that's underestimating that you can think of this one as kind of netting out a little, which is why this one's giving approximate. Okay, remember our real area, our computed area is pi 3.14. Okay, in most cases when you're doing this though, you're not going to be able to compute an exact area, okay, because you won't have a formula for the shape of the curve. Okay, so the only reason I'm doing this is I'm comparing the different approximations so you can see that some are better than others. Okay, so let me stop and ask everybody understand the right endpoint and the midpoint rectangles. So basically, if you've got any questions, ask them now. Okay, everybody understand how I got the right endpoint and midpoint rectangles. Are we good? All right, if you just give me a yes or a no, that'd be great. Anybody questions on endpoint and midpoint? Okay, I'm a little confused. Okay, can you kind of articulate your question a little more? Are you confused with how I'm finding the rectangles, or are you confused with the arithmetic? Right, again, as far as building and how I'm finding them, okay, that's usually where people are confused. So let me go slide back up to the picture. Okay, this picture here on the left side of the screen is what's called a right endpoint rectangle. Okay, again, if I'm going from 0 to 2, all right, I want the right endpoint, this first rectangle, namely where x is 1, I want that to sit on the curve. So that's why I'm building the rectangle the way I did, okay? You recall when I built a left endpoint rectangle, I had the left end of the rectangle sitting on the curve. See the difference? With this, the left side is sitting on the curve, the right side's hanging out. It's too big, okay? With the right endpoint rectangle, the rectangle's too small. It's totally inside the curve, okay? With the midpoint rectangles, I'm trying to hit the middle of this rectangle, get it to sit right on the curve. Same thing with this one. I'm trying to build a rectangle in such a way that, again, the rectangles all have to be 1 unit wide. The only control you have is with the top of the rectangle, okay? You're either going to make the left point sit on the curve, the middle of the rectangle sit on the curve, or the right side sit on the curve, okay? Let me stop and make that clearer. Okay, good, so a little clearer. Okay. So one thing you can do here, you can see these are still not terrifically accurate, um, okay? They're still not really good estimates. So what can you do to make the estimates better? Well, what you can do is you can increase the number of rectangles, okay? And that makes the calculation a little harder because, again, with these nice big fat rectangles that are 1 unit wide, when I'm finding area, I'm just multiplying by 1. So if you increase the number of rectangles, you have to remember you've changed how wide they are now. They all have to be the same size, right? But if I put more of them in here, they're going to be skinnier rectangles. So maybe they'll only be a half a unit wide instead of 1, okay? So what I'm saying here is I can increase the accuracy of my estimate by increasing the number of rectangles, okay? Here's the same area computed with 4 left endpoint rectangles, okay? So essentially, now I have rectangles that are half a unit wide, okay, here. And again, I'm substituting in the right-hand side of the left-hand side of each of these rectangles. So the first left-hand rectangle is going to have its left corner on 0. The second one will have its left corner on 1/2. The third one will have its left corner on 1. And the fourth one will have its left corner on 1 1/2. Okay, no, it's confusing. I'm going to show you a picture in Desmos in a minute, and I hope I'll be able to get that to work the way I want. Okay. Here, I just want to show you, once I add up all of those 4 rectangles, you can see I'm getting much closer to pi. Okay, I'm getting a much, much better estimate. Okay, much better estimate. Okay, let's take a look at this picture first before we move on to Desmos. Okay. So now remember, what I've done is I've made the rectangles skinnier. Now they're only half a unit wide. And because they're skinnier, I can fit more of them in the same space. So here's the same curve and the same distance from 0 to 2, only the rectangles are now half a unit wide. Okay. And again, I'm plugging my left endpoints in to find the area. So again, I have this height is 2, right, times 1/2. So this rectangle will have an area of 1 square unit. Okay. This left rectangle has its left endpoint on 1/2. So I have to plug in 1/2 to my formula. Okay, the square root of 4 minus x squared. Okay, to get that value here. Okay, and then I'm going to multiply that by 1/2 to get that area. Right? Then I'm 1 to get the height of that third rectangle. This is the one that gives me square root of 3, okay, times 1/2. Okay, and then lastly, I have the last rectangle is sitting at 1 1/2 on the left corner. Okay, so I have to plug in 1 1/2 to my formula to get the y value. That's the height. Okay. How about this? Is it making sense with more rectangles? Okay. Okay. You see how I'm getting the heights? Again, you need to use the function to generate the heights. Okay, I'm going to stop here and ask, is this making sense? Anybody, any questions about how I'm getting the heights of the rectangles? Okay. Here's the general idea that connects this to calculus. So far, we're just approximating areas, okay? If I make rectangles even skinnier, what you want to notice is they're going to hang out less and less from the curve, okay? They're going to hang out less and less from the curve, and they're going to approximate the area under the curve better, okay? So here's a statement, okay, about the exact area, okay? If I add up, remember this is some notation, this sigma means add up these n rectangles, okay, where I take the height of the rectangle and the delta x is the width of them. And I let the number of rectangles get infinitely large, okay, I'm going to hit the exact area of the curve, okay? So again, if you let the number of these little rectangles get infinitely large and they get super, super skinny, what you've done is you've actually created the integral of the area under the curve. We created the same thing as the calculus answer, and that's because we're taking the limit, okay? So when you can actually do this, you created something called the definite integral of your function from, and it's given the area under the curve f of x between the x-axis from A to B, okay? So again, let me stop here and let me ask, understand the of making the rectangles super skinny and lots of them, okay? Everybody understand the idea of the limit as n approaches infinity. Basically, what I'm saying is I'm making many, 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 many really skinny rectangles, and that's a better approximation. Okay, better approximation. Okay, great. I think this might be a good place to switch over to Desmos, and let's see what we have in Desmos. So again, this screen and try to bring up Desmos. So give me a minute, and hopefully I can do this without breaking anything. Okay, so what I have here, I'm not quite sure where to put this. I have an app that somebody built in Desmos, okay? And again, it has a function here, f of x, that we want to find the area under, okay? And this, if you look up Riemann sum Desmos, you will find this application. And it's really cool for playing around with these approximations, okay? Again, these sums of the areas of smaller and smaller rectangles, these things are called Riemann sums. Here's the word up here, okay? And again, it's named for Georg Riemann, who was a German mathematician, okay? So basically, here is a function. It's a fourth degree function, and I want to find the area under it between -1 and 2. I'm starting out with rectangles that are 1 unit wide. You can see down here, and the app lets me control that. Okay, the app lets me control that by some of the keywords over here on the left. Sorry, I'm just trying to position things on the screen, okay? Here's the Riemann sum, okay? And basically, it lets me decide whether I want endpoint, right endpoint, or midpoint rectangles by changing this value, okay? When C is 0, you can see I'm setting up for left endpoint rectangles, and you can click on these to see what the Y values are, okay? So for this rectangle, okay, the height of it is 1.5, the width is 1, so this area is 1.5 units. This rectangle has a height of 3 and a width of 1, so its area is 3 units, square units. And this last one is the same as the first. It has a height of 1.5, so its area is 1.5 square units. So I have 1.5 plus 3 is 4.5 plus 1.5, 6 square units is my approximation. And if you go down here, they do show you the approximate sum. See down here is 6. Okay. So I just want to show you switching this to right endpoint rectangles for a minute. Let's see what that looks like. I'm going to make this a 1. Shift now so that the right endpoints sit on the curve. Okay. And if you want to look at that, that's a 3, 1.5, 3. So this is going to be a much bigger approximation of the area under the curve, okay? And why is that? Well, you see this rectangle is really overestimating the area under the curve, and so is this one. Okay? Last but not least, I'm going to change this to midpoint with a 0.5. Okay, and now you can see the middle of each of the rectangles is sitting on the curve, and that's what I'm using for the height. Okay, and that's 6.09. Okay, none of these are terrific approximations. Okay, but you can see that they give me approximate values of the area under the curve. Okay, let me stop and let me ask everybody, are you understanding how the app works? Okay, are you understanding what Desmos is showing here? How's that working? Okay, can you give me a shout out? Yes or no? Is this clear? All right. And again, you have access to this. This is out there if you just look for it. If you want a link to it, I can include that along with our video link. And then that way you have no trouble finding it. You can just get to it right away. I think that's what I'll do. Okay. All right. I'm going to go to the left endpoints, which was a 0. Okay. And then let's increase the number of rectangles, okay? If you take a look over here, number of intervals, I've just set them to be 3, okay, because then that way I have them to be 1 unit wide, okay? Let's double the number of rectangles. So I'll make them a half a unit wide. Okay. Now you can see the left endpoints of each of these rectangles are sitting on the curve. Okay, this should give me a better approximation rather to the area under the curve. Okay, so this is giving me a better approximation to the area. And again, you can see now I have 6.04. Let's double the number again. Okay, so now instead of 6, I'm going to have 12 rectangles. Okay, do you notice that these left endpoints, the shape is starting to look more and more like the shape of the curve? Again, you can click on the left endpoints to see what the heights of the rectangles are, but it'll compute for you over here what the area approximation is. Okay, so again, I'm trying to show you the left endpoints by clicking on the heights. All right. I'm going to just double them one more time to get them even smaller. Okay, and you can see the more and more rectangles I add, the closer and closer I get to the shape of the curve. Okay, and basically, if I let this number get very, very large, I'm going to actually approximate the area of the curve very closely. Okay, and essentially, when you let the number of these rectangles approach infinity, is when you're getting this definite integral that's giving you the area between 1, -1, and 2 under this curve, okay? And you can see now my area is 6.21, okay? Is everybody understanding the more and more rectangles, okay? Everybody seeing what happens as I increase the number? Okay, is this making sense? Everybody seeing what happens as I create more rectangles? All right. So again, right, if we were to, let me introduce the idea of a definite integral, okay? And you can understand that where we're headed, and that'll be in the next lesson that we actually talk about this. As I let this get really, really large, okay? Let me let n slide way over. Look at how many rectangles. Do you see how it's getting closer and closer and closer? Now it looks just like the area under the curve, okay? And you can see I'm at 6.277. Which is probably a really good approximation of the area under the curve. Okay, that's what I wanted to use Desmos for, so you can see why increasing the number of rectangles gives you a better approximation. Okay. Now, when the next lesson that we go into, which is 15.4, we'll talk about taking Riemann sums and using them to build definite integrals. Okay, so we're not going to quite go there today. We're just going to see if you can build one of these approximate areas. Okay, so let me go back to my notes. And let me check. I'm not seeing any questions, so I guess it's okay to move on. So just to kind of show you, okay, here is a definition of this definite integral, the thing that's going to give us a number that's the area under the curve. Okay, it's called a definite integral, and it's always defined on a closed interval. Remember, these are both x values. Okay, here's the way we're going to write it. Okay, it's got the integral summation sign, but do you see now I have what are called limits on the integral? Okay, the lower bound or the lower limit is the left-hand x value. The upper limit is the right-hand x value. Okay, you put your function in here, okay, and dx, okay, this is exactly defined as that Riemann sum, okay, as you let the rectangles get super, super skinny and you create lots and lots of them, okay? All right, so this is just the calculus definition of this definite integral, okay? Now I realize it's not terribly satisfying. You see the definition. We've spent a lot of time playing with that one function f of x equals the square root of 4 minus x squared, right? And we wanted to find the area between 0 and 2. And we did a whole bunch of approximations of it. Well, what would the definite integral give us? Remember, we had a formula for the area of a circle because it was a quarter circle. So we were able to compute the exact area. But let's figure it out with a definite integral. I'm going to show you how to do this in Symbolab. Symbolab, remember, is an algebra and calculus engine. You're welcome to use it. It's not cheating. I want you to understand how this works, okay? And Symbolab will show you steps. So I'm going to minimize this, and I'm going to go into Symbolab. This is over here, okay? So I have Symbolab over here. And you can see it gives me a whole bunch of calculus choices up here. Here's our friend, the antiderivative or the indefinite integral. Remember, this is the antiderivative that returns a function that generates that total value. Here is the definite integral. See over here? It has bounds where I can put in the left-hand side, the left-hand x value I want to sum from, and the right-hand value I want to sum from. So I'm going to put this in my bar, okay? And I'm going to use the function that we used in our example, which was the square root of 4 minus x squared. Let's see how this works. Okay, and then I have dx. Okay, that was our function, our quarter circle. And we wanted to find the sum from 0 to 2. Okay, we approximated this with Riemann sums using left endpoint rectangles, right endpoint rectangles, and midpoint rectangles. Okay, we know the answer is pi because we were able to calculate it with the area of a circle formula. So let's see what the definite integral gives us. Again, anybody have any questions on the setup of the integral here? Let me just pause here and say, any questions on definite integral setup? Everybody see where I'm getting the 0 and the 2 from? Remember, those were the x values we wanted to find the area between, okay? before I press go, I want to know if anybody has questions. We're good? Okay, there's only 3 of you, so don't hesitate to ask. Okay, good. Let's see what we get. Go. Right. Again, it takes a minute. And you can see here is the answer. It says the answer is pi, 3.14159. Okay. And again, it's going to integrate with methods that we're not going to use. I'm just showing you that we can get the same answer. This also works on your TI 84 actually will help you evaluate definite integrals. Again, basically I can talk you through it. I can't bring up an emulator because those things are difficult to install on a laptop, but I can kind of talk you through it. Okay, you're more than welcome to use Symbolab if you want to see how to approximate them. Okay, on your TI, okay, if you look at your TI, okay, you want to type second trace, which is your calc menu. Okay, everybody try second trace. And if you look at number 7, okay, number 7 is a definite integral. It requires that you have a function already in y equals. Okay, so again, if you put this function in y equals, okay, then you can use number 7 on the calc menu to tell you the area between the x-axis and the curve. I will give you a warning about using your calculator for finding areas under a curve, okay, is if the function drops below the x-axis, those areas will be negative and they'll net out, so you won't get a correct value. As long as the curve is completely above the x-axis, like our example, though, it will work. Okay? So quick check, any questions about using Symbolab? Questions on using Symbolab for integrals? Are we good with this? Okay. Right. And again, it works on your TI. It's just clunkier. Okay. Symbolab is a little bit more of a modern app. Okay. Good. All right. Let's go back to the notes. Okay. All right. And again, here is, I got his first name wrong, Bernard Riemann, okay, who developed the idea of a Riemann sum, okay? And again, that's the sum that when you take the limit of it, you get the definite integral. So what can we use this for? Okay, why would you care about a definite integral? Okay, you care about it if you want to find the total change of a function, okay? So let's say, for example, you had a marginal profit function. You actually have the rule for it. It's a marginal profit function. You want to find, all right, great. This was my marginal profit for the last year or so. It was the model for it. I want to find my total profit from the first quarter to the third quarter of this year. Okay. Well, what you can do is you can integrate your marginal profit function, and then you can put bounds on the integral from quarter 1 to quarter 3 and evaluate what came out of the integration here. Okay, and that will tell you what's the total profit between those 2 quarters. Okay, so that's kind of where you would use it. Okay, if you have the model for a rate, you can use it to generate a total value. Okay. Let's take a look at an example here, and then I'll have you play with some Riemann sums. Okay. Let's say we know oil is leaking from a machine in a factory. So we have a problem, okay? And let's say we know it's leaking in cubic centimeters per hour. Cubic centimeters is a volume measurement, okay? Per hour, the per is telling you you have a rate, okay? That's important. If they don't tell you the word rate, you want to look for the word per, okay? And they're given by the following table, okay? So Y is the amount of oil leaked in cubic centimeters. 0 is the time in hours since we first noticed and started measuring what's coming out of this machine, okay? So we noticed we have 15.2 cubic centimeters on the floor when we started measuring, okay? Then in the first hour afterwards, we have another 18 cubic centimeters. The second hour, another 18.8. So these Y values are like the heights of the rectangles, okay, in the Riemann sum, okay? So we have 12 left endpoint rectangles, okay? And the width of each of them is 1 hour, okay? So suppose you want to approximate the total amount of oil leaked, okay, over the 12 hours, okay? Again, you're going to add up the areas of the rectangles, right? So you've got the first one has a height of 15.2 and a width of 1, right? The second one has a height of 18 and a width of 1, and so forth. So it's just like adding up all these heights, okay? So you basically have about 187.8 cubic centimeters of oil leaking out of this machine in the 12 hours you've been watching it, okay? The exact value is given by this integral from 0 to 11 of whatever this function is, okay? Now, this is the next piece. This is what we're going to evaluate in our next section. But let me stop and ask here, everybody understand the oil example? Okay, everybody understand the oil example? Okay. Okay, what I would like to have you do is to try to actually compute an approximate sum yourself. So I'm going to try to stop sharing my screen here and see if we can go back to this, right? And hopefully I can get an example. I guess the best way to do it is to bring up an example in Desmos. It'd be easiest for you to see than have me drawing on the board, okay? All right, so let me see if I can bring up an example in Desmos, and then I will try to hide the answer so you guys can play with it. Okay, so let me see if I can get back to Desmos. So that's what I'm going to try to do. Okay, I'm going to try to alter what's here and have you compute it. Just give me a sec. And let me see if I can zoom out. All righty. I'm going to click on these so you can see them. Okay, I think I'm set up for you to go. Let me come back here and share my screen again. All right, folks, ready to go. I'm sharing Desmos with you now. And what I'd like you to do is you try and compute the approximate area under the curve, okay? Sharing, and let's get back to Desmos. Here we are. All right. All right. So here's our curve, Okay, you can see I'm using left endpoint rectangles, so the first one won't fit, okay? And I'm trying to show you the values on the left endpoints. Okay, you can see my function up here. Okay, so here's what I need you to do. Okay, it's y equals x squared. So I need you to compute the Riemann sum value here. I want to know what's the approximate area of the blue rectangles. Okay, everybody understand what I'm asking? Okay, everybody understand what to do? And again, I'm showing you the left endpoint so you don't have to calculate anything. Again, they're all 1 unit wide because this value here is 4. It's difficult to fit the whole thing in the screen. In case anybody has questions. Okay, but again, these rectangles are all 1 unit wide. This is a 4 down here. And I'll calculate the answer with you, okay? Okay, as soon as you have an answer, okay, for the area in square units, type it in to the chat box. Okay. So again, let's wait for some more answers. There's only 3 of you, okay? So don't hesitate to type in your answer. Remember, the height is the y value of the left endpoint, okay? Okay, so I'm going to wait for a few other people to chime in. Right. 14 as well. Awesome. Let me scroll down and see what they got. Yay, they got 14. Good for you. So you're understanding the strategy. Okay. I'm going to switch to right endpoints and let's try it again. Okay, so I'm going to switch to right endpoints. Okay, and hopefully we can see those. Right. I can show you the ones that are on the screen. You're going to have to find the right endpoint of this last rectangle yourself because I can't display it. It's too high up. Okay, so let me show you these. You can get it from plugging it into y equals x squared. This x value is 4. Okay, so try it with right endpoint rectangle. When you get an answer, just type it in the chat. You want to find the area of these right endpoint rectangles, okay? Because they're also approximating the curve. We just want to do the same thing, Yesenia, only using the right endpoint rectangles. Okay, and this last one, the one that has its right endpoint on 4, you're going to have to figure out what the y value is. Okay, we'll wait a minute for all 3 of you to sign in. Don't hesitate to ask questions if you're stuck. Okay, where are you stuck, Yesenia? Can you be a little more specific? Okay, we're doing the same thing. These are 1 unit wide, and the heights are now given by the right endpoints, the y values. Okay, so you've got a rectangle here with a width 1 and a height 1, a width 1 and a height 4, a width 1 and a height 9. And this one, you have to figure out the y value on. And again, you can do that using this, okay? You plug in 4 for x, okay, and you square it. So the height of this rectangle is 16, okay? Is that better? And we're just going to add those areas together. Okay, so here's what I'm getting. The first rectangle's 1 square unit, then 4 square units, then 9 square units, then 16 square units. Right? And if you add that up, you get 30. Okay, everybody getting that? Now, please remember, these rectangles, as they get smaller and smaller, they're not going to be 1 unit wide. So you can't just always look at the height of them. Sometimes you have to look at the width as well. It just gets messier. Okay? Is everybody clear on this example? Okay, please don't hesitate to ask if you're not sure how to build these, okay? I want to make sure we're good with this. There are plenty of examples in the homework for section 15.3 that go over problems like this, so you can get a chance to play with them. And again, I'll make sure you have this link to this Desmos app so you can play with that. Okay, that's the most helpful thing to do. Right. Okay, well, again, I really don't have more material to share with you on this topic because the next step is moving into actually doing calculus with this. Today's lesson was more about approximating with Riemann sums. Here's what I want to talk to you about. I want to talk to you about our next test, which is online in My Math Lab. Okay, so I want to show you our My Math Lab course over here. Okay, and I'm also showing you our course notes and videos. If you scroll all the way down to chapter 15, which is where we are right now, you will see test 3 practice with worked out answers. Okay. These are questions that are exactly like the online test 3 that's in our course. I set the due date on test 3 to be the same as the due date would have been in our class where we're still meeting in person. However, all class due dates on everything are pushed out to May 15th. You do not have to do this test now, okay? Although if you're ready to do it now, that'd be great. What I'm going to be doing in our next class, okay, when we meet next Tuesday, is I am going to be going over test 3 practice, the worked out answers. So please, between now and then, get into our course, take a look at the questions, okay, and the worked out answers before you attend the online class on Tuesday. And I'll be happy to go over whichever ones you want to see in detail, okay? Just be forewarned, I really went into a lot of detail explaining these because I know we aren't doing exams in class, right? So I don't want anybody to not be clear about anything. So this is, they're not that complicated, okay? I'm just explaining a lot, okay? So let me go and show you where the test is. Okay, I'm going to be basically going over to assignments. Okay, and if I scroll down in assignments, you'll see the test. Here it is, test 3. Okay, it says you have 0 out of 2 attempts to do it. There is no time limit on this test. Okay, if you need to end in the middle, just close your browser window like you would on a quiz, and you should be able to pick it up when you left off, okay? But you have 2 complete attempts, and I'm going to be asking people to please do work on paper, and then if you can, scan in your work or take pictures of it and email it to me so I can give you partial credit. Remember, my math lab is very picky about the way you answer things, and you may have the answer correct, just my math lab didn't like the way you typed it in. I want to be able to give you partial credit, okay? And can only do that if you share, okay? So let me ask, okay, anybody questions about the exam? Let me ask that. Any questions about the exam? Okay. Okay, so again, the review is going to be in our next online session, okay? I will make sure to send out not only an invitation to the next online session, but I'm going to be sending out an email to everybody, and I will put the blank questions as well as the solutions in that email so people don't have to chase around for it, okay? So going back to my main window screen, let me go back here. Anybody have questions on anything? Any questions at all? Anybody questions at all on anything? Okay. All right. Thanks, Vicente. All right. If you guys don't have questions, that's really all I wanted to cover today in class. Again, I recommend that between now and then, you take a look at those review questions, and I will be going over whichever ones you want to see in class next time. Okay. So if you don't have any other questions, feel free to drop off the conference anytime you're ready. I'll see you next time.